Dave leads the Aerosol science team within ERG, so he's going to talk to us about measuring aerosol composition. Thanks, Dave.
Thank you. It switches on automatically. Fantastic. Well, it's a real pleasure to be here this afternoon and to see so many friends and colleagues who I've worked with for, well, over the last nearly 30 years and who have been here almost from the very start and certainly from when I first turned up. A lot of my focus since I joined in 1995 has been measuring the aerosol composition, the parts of PM that give us indications as to where it comes from. And today I'm going to focus on how we do that and how we use that information to help inform policy. Okay, so aerosols come from lots and lots of different sources. They come from anthropogenic sources like cooking, so we'll start over here on your left. Wood burning you've heard about, industry and agriculture and traffic. They also come from natural sources, forest fires, crustal material, so we get Saharan dust that's blown out into the Atlantic and then comes back and lands on us a few days later. Or we get sea salt into our atmosphere from the breaking of waves and then it's transported into us. Lots and lots of these particles are emitted, or they're emitted as gases and particles into the atmosphere, and in the atmosphere they react and form new particles. So it forms this complex mixture that's changing and evolving and getting bigger and smaller. And then it transfers downwind and we measure it at our monitoring site. Or you breathe it in as people in your different environments. And it all goes up and down, you experience it in different ways. And this is really challenging to understand, really challenging to explain. But what do the measurements tell us? So if at one of our monitoring sites, we measure the composition of PM, and this is a PM 2.5 example. This is what our measurements tell us. About half of it is organic aerosol, organic mass, and that we can use source apportionment to split into different sources. So it tells us about a quarter of it is, about 20% is made up of anthropogenic sources, so that's cooking, traffic, wood burning in about equal measure, and then 25% is from secondary. So that stuff that's been emitted as gases into the atmosphere, undergone those chemical transformations and formed particles. Most of the other half is secondary inorganic. So these are again emitted as gases, so they're emitted as NOx or SO2. And again, they're reacting in the atmosphere, combining with ammonia from agriculture to form our inorganic aerosols like ammonium nitrate and ammonium sulfate. And about 10 or 12% is black carbon, which is emitted from diesel vehicles or from wood burning. So that's what we know, but we know it varies over time and it varies over space. Now, this presentation is themed, and we're trying to develop targeted mitigation. I've split this into 4 key challenges. The first thing is we have to quantify those sources using the measurements that we have. We then need to inform abatement policies so that we can tackle these sources. We then have to assess progression in tackling these sources, and we have to establish the health effects from these different sources. And I'm going to tackle these one at a time. So we'll start with quantifying the sources, and this is a measurement seminar, so I'm going to go into quite a lot of detail on this one. So we have our 2 super sites. Marylebone Road, which many of you will be familiar with, is on your right-hand side, and on your left-hand side, and on your right-hand side, spinning around, is drone footage from actually Tim Baker's son, of On Oak Park, which is our new site at the urban background. So we have this contrast. We have urban background, which you can see is representative of what people are exposed to when they go to the local park or in their back garden. And then we have our roadside site, Marylebone Road, which is that heavily trafficked location right in the centre of London. We also work with many of our colleagues around Europe, and this is really important because super sites, when they're combined together, they become even more super. You can do so many more things. You can understand where particles come from long distances, how they're changed through different circumstances. So the sites in London sit within a broader European network that's under the umbrella of Actros and a European project called RI Urbans. And there are now 20, 30 of these sites around Europe. And super sites are being included in the new draft EU Air Quality Directive. So they're going to be an important way that we recognise and understand pollution in the future. When we come to look inside these sites, they contain a lot of instrumentation that tells us a lot of detail. So I've split the instrumentation up into aerosols, gases, and meteorological measurements. And what we try to do as best we can is to match the measurements we're doing at the roadside with the measurements we're doing at the background. So we have all these different measurements, and then you can see on the right-hand side what it looks like inside one of these super sites. I'm going to concentrate on what we're doing to measure PM. So if I think about PM, it's there in that mixture, and that's represented by those little dots in the middle. Imagine that's a little picture of the atmosphere or what we're collecting onto a filter if we were sampling them. We can then split it up into different categories. So our organic aerosol and our inorganic aerosol are measured by our ACSM, which is up there on the left-hand side, and our metals, which tell us about marine aerosols or what's coming from industry or what's coming from those non-exhaust sources that we've heard about, is measured by our XRF instrument, our X-ray fluorescence instrument on the bottom left-hand side there. And then our black carbon is measured by the ethylometer. And when we combine these three metrics, or these three instruments, we can measure pretty much the whole of our PM2.5 mass. And that's a really powerful analysis. I'm going to give you a couple of examples of what we can do with that. First of all, we have to take those measurements and we have to undertake some receptor modeling. Now, this is where you take those complex measurements and you combine them mathematically to help understand sources. There are different ways of doing that. You can do it using chemical mass balance, which is on the far side over here. And this is where you understand a lot about the source. So if you know exactly what your industrial source is, you know exactly what's coming out of the chimney, then you can look exactly for those combination of pollutants. But we don't know that. The atmosphere is a little bit unknown to us. So we're looking for a whole range of sources, and we don't know exactly what's there. So we use these multivariate statistical models that are over here. And we use something called PMF, positive matrix factorization. And this takes all of our data and turns it into a source for us. Ian Chen, who's in the audience, produced this paper here, which combined all of those monitoring sites from around Europe. But a great deal of work in combining 22 different monitoring sites from around Europe to source apportion that organic aerosol. And here you can see, as I showed you earlier, that about half of our PM that comes from, well, measured in any location around Europe is organic, and organic in origin, and split roughly between those secondary organic aerosols and local primary aerosols. Of course, it varies a little bit on where you're measuring it. If you go to the site in Finland, it's quite close to a coffee roaster. And you find actually organic aerosols from the coffee roasting process. And this is why it's important to measure in all those different places, because they will have different influences. But if we concentrate on London and look at the PM1 in London, concentrations are around 9 to 10 micrograms per metre cubed. About 10% of that is elemental carbon, 40% inorganic aerosols, and about half of it, those organic aerosols that we've talked about. I've included in here some data on non-exhaust. Now, this isn't published yet. Anya Tremper's working this up at the moment. But again, we're focusing on our two sites in London here, Marylebone Road on your left and Honor Oak Park on your right. This data spans the COVID period. So what we've done is we've split our analysis to before lockdown and during lockdown. And of course, during lockdown, there was a big change in traffic flow. And we expected to be able to disentangle our analysis based on the changes in traffic flow. So on the left-hand side, you see Marylebone Road, and we're able to identify tyre wear, brake wear, and you can see that tyre wear doesn't change, but brake wear drops during lockdown. We're hypothesising that tyre wear doesn't change because the traffic speed's increased. The faster the traffic goes, the faster the traffic moves, the higher the rate of tyre wear. Of course, there's lower traffic, and therefore it's not braking so much, and that's why brake wear reduces. So we're able to detect these changes using our source apportionment analysis. Okay, moving on to assessing progress. Informing abatement policies. So I want to concentrate on cooking here. Normally, when you develop an emissions inventory, you start with a spatial representation, you understand what your emissions are, you then model it, and then you compare it to your measurement. But with cooking, we don't really know what the emission strength is or what the location is. So we have to reverse this and go from our measurements back towards our inventory. We did this with a group in the University of Edinburgh and produced a UK-wide map at 5 kilometre resolution, and that really told us that the concentrations were highest in urban areas, as we'd expect. However, a 5 kilometre square grid map doesn't really help you inform abatement policies. So we worked with the local modelling team, and we've produced a London cooking emissions inventory, which is at 1 kilometre resolution. And that's going to allow us to identify locations and form abatement policies to help us develop abatement policies to tackle these emissions in the future. Moving on to assessing progress. And of course, we can use our source apportionment measurements to understand how things go in the future. We can look at long-term trends, etc. But what I want to show you now is an episode tracker that is hopefully going to start playing. Okay, so this is something we've developed for On Road Park measurement site, which allows you to look in detail at the composition of PM2.5 in real time. So it goes a little bit beyond what you normally see on our measurement sites. So you can find the link to this on our website, and you can look at this, you can focus in on particular episodes and understand what is going on at any particular time. Here I focus in on a period of transboundary air pollution, and you can see that it's made up of organic and inorganic aerosols, as we've talked about. We've also linked with our colleagues at the Met Office to provide back trajectories, so you can select the dates you're looking at and find out where the air mass was coming from at those particular times. You can see that during those high concentration periods, air was coming in from Central Europe. Finally, I'm going to look at what we're doing to establish health impacts. So what we don't know is what parts of PM cause the most health impacts. So what we're doing now is we're linking our more detailed measurements of chemical composition and our more detailed measurements of sources to population exposures. And here we're doing it with panel studies. So we're taking people with pre-existing lung diseases onto the London Underground and measuring the concentrations they're exposed to. And we're taking people with asthma, putting them on bikes, making them cycle next to roadsides, and looking at their response in different environments. And that's going to help us understand which of these components of PM are more important for health. I want to finish with some take-home messages. Sources and exposure are very complex. We can only understand these by measuring PM composition at high time resolution and linking those to sources and concentrations. Doing it in this way has enabled us to identify and quantify these sources and look at also emerging components or sources like cooking, and that can lead us to inform policy development. By tracking the episodes and long-term trends, we can provide this information to stakeholders, and that can be both policy stakeholders like DEFRA or the Environment Agency, but also individuals so they can make changes. And finally, we're working with our colleagues in the health area to link those sources to health exposure. Now, I want to finish off by saying that this is not all my work. I rely on an excellent team, the Aerosol science team, who are pictured along the bottom here. And if you want to find out more information, you can follow us on the social media channel formerly known as Twitter. Thank you.